Hey everyone, welcome back. Today we will walk through the Hub-Monorepo and a bunch of its packages. I've already done Shuttle. So what happened is that I was building out a backend, a Nest.js based backend to support some of the Farcaster apps that I have written over time. Like I can quickly give an overview. Uh, Yes, so these are the different apps that I've written with multiple Next.js projects. So what I was trying to build out was create one unified backend with a sign in and Farcaster option that can basically give you access to this suite of apps. Now, in that particular thing, I ran into a bunch of issues with respect to even like Farcaster's auth kit, wherein this is written primarily for React and Next.js. And Next.js is what serves as a server-side thing. So I'm trying to build out a Nest.js version of it where like any front end can interact through this Farcaster auth kit and get a JWT that then they can use to access the APIs on the unified backend that I'm building out. This was the first problem statement. The second problem statement then came out to be something around using Neynar's APIs. So now Neynar has something called managed signers. So managed signers, they have a pretty nice guide and code example given here. This one, how to write data to Farcaster using managed signers. So I replicated this whole thing for the Next.js app and it worked perfectly for me. But I wanted to understand deeper as to how this piece of code is working. And then I eventually ran into the fact that they are also using under the hood a bunch of Hub-Monorepo related packages. I think the core as well as the Node.js package from Hub-Monorepo. So I thought I'd deep dive into this whole thing and I'll create a quick video on top of it as well, so that yeah, if you need to go through it, it will be easier for you as well. So today's objective is diving deeper into Hub's Monorepo and these essentially these 2-3 packages that are remaining. Shuttle I've already done. The example app of Shuttle is remaining. I'll probably do that in another video, but it's relatively straightforward. Whatever has been written inside the package, it's just an implementation, just calling those bunch of functions in a sequence. Alright, so let us get started. Right, what I wanted to show was this piece, that in Neynar I found they have used Farcaster's package as well. Trying to find out where that was. But yeah, I went like deeper into managed sinus and then therein I saw. Check it out quickly. So this is like a bunch of exploration kind of a thing. It will not be like very linear. I'll be jumping between different packages and different things to figure out what exactly is going on under the hood. So you need to be familiar with overall Farcaster structure and some of Neynar's APIs as to how they work. Yeah, this is VM local EIP 712 signer Farcaster Hub Node.js. To generate a managed signer. Alright, so let's get started. First, I'll try to figure out how Neynar is implementing these managed signers. For that, I need this particular piece of line. In fact, what I can do is we can start with the core package itself, since that is the topic of this video, and then move on from there. So kind of build out bottoms up. So you can go to Hub-Monorepo in Farcaster XYZ github.com, GitHub profile, and then you can get to the core package. Shared hub related method and classes. Okay. Let's get into the SRC. And there is a lot of code. We'll have to go through this one by one. So let's figure out protobuf, builder, bytes, crypto errors, ETH, factories, signers, time, validations, verification, user improve, and limits. Alright. Where do we get started? I really try to find out some sort of types interfaces and start from there. Import asterisk as protobufs. Okay, so I think protobufs is the starting point here. Yeah. Generated hub event. Oh, I hate when this happens. Hub event protobufs, on chain event protobufs. Generated protobufs is the first piece that we should be looking into, because this would be the first thing defined from where everything else would be originating. Alright, so there are a bunch of protobufs defined. This will be consistent very much with the overall Farcaster protocol itself. Message. Okay, so the overall Farcaster network talks in terms of messages, and these messages have different types. Like it can either be like cast, reaction, username verification, etc. So let's just keep moving downwards into it. Yes. Message. So I have a message protobuf, which in turn takes username protobufs, username proof. Let's get into it. Import long from long and 0 from protobuf js/minimal. That's fine. Username type. Username type is none. It is fname or it is an ENS on L1. So these are 3 username types. None. Fname. ENS on L1. Username type from JSON. So give it a JSON object, which is of any type. It returns a username type. This is just a bunch of case to figure out which username type is being called for. Case 0, nothing. Case username type none, you get this. Fname ENS straightforward. It's basically converting from JSON into this protobuf, and from this protobuf into JSON. So just the inverse of this. That you take the username type as argument, and based on the different cases it will return the specific string. Username proof. Okay, so once you generated your username username type, another thing that you can generate here is your username proof. What is going on? Yes. Then in username, you need to provide proof that you own that particular username. So timestamp, name, owner, signature, FID, type, right? So I think this would be the username, this would be the owning address, the signature, your FID on Farcaster protocol, and the type of it. Create base username proof. Okay, so this is the interface, basically defining your data model, and then this is a function that returns a username proof. All you need to do is return, when you call this function, you return a timestamp 0 and just array, basically placeholders in a way. I think this function would be overwritten somewhere. Username proof, encode message username proof, writer dot create. So this username proof has encode decode from JSON and two JSON functions, right? So it takes in a username proof, or takes in a message which is of type username proof, passes in a protobuf writer, and then using that, depending on the values of the message, it does a bunch of operations, basically encodes it into a protobuf. Writer.uint32, uint64, message to timestamp, name length is not equal to 0. Okay, it's checking if the timestamp is not 0, name length is not 0, owner length is not 0, then writing it. I'll quickly check with ChatGPT as to exactly what this piece is doing. Is it writing to some sort of a protobuf packet or vice versa? Let's quickly find that out. Yes, I often use ChatGPT in this one to basically figure out some of the unknown pieces of code. Part of Typescript module using protocol buffers with protobuf.js library, serialization, deserialization of data in protocol buffer formats. Fine. Import statement, long library, 64-bit integers, straightforward, hem0. Minimal version of protobuf.js, work with protocol buffers in JavaScript. Common functionality required for encoding and decoding messages, right? Username proof, Encode method for a protobuf message username proof. Alright, so your username proof for the protocol buff message. This is your protocol buff message. This is creating a base version of that. And then this is encode method for protocol message username proof. Takes two parameters, message. Right, contains the data to be encoded, writer instance from protobuf.js to write the encoded data. Conditionally encoded if it has a meaningful value. Fine. Timestamp is not equal to 0. Encodes the timestamp field. UN32 call specifies the field number and type. Field 1 type UN64 in protobuf variant encoding. This is what actually encodes the timestamp. Alright. So it's some sort of a encoding in like a serialization thing wherein whatever message packet you have, it would encode it as a protobuf message. Same thing. Field number 2 with bytes. UN3218. UN3226. What is interesting to me is 8, 18, 26, 34, 40, 48. Alright, so what I want to understand here is what is the significance of uint 32.8. So your original protobuf username proof would be assigned like in one giant string of bits, sequence of bits. It's assigned different positions, like where this is starting from, where this is starting from. I think that is what it is trying to signify. How does it calculate is what I'm interested in. Each field in protocol buff message is identified by a unique number assigned in the schema starting from 1. This indicates the type of data stored in the field. Okay. Tells the parser how to decode the bytes into the appropriate data type. So what I'm trying to get at is you have a interface, this user name proof, and you have timestamp name owner signature, timestamp name owner signature, and so on. So it will be like this, and it's encoded as a protobuf message. I'm just randomly drawing dashes. Owner is still here. Then you have your signature. So this entire thing will be your encoded protobuf. and this is what is happening with writer dot uint 32.8 dot whatever the rest of it is uint 64 timestamp. This piece is just identifying this field. Similarly, uint 32.2018 is identifying this piece, like this length in your final encoded message. So where to put in the name, where to put in the owner, where to put in the signature, and the decoder will then use the opposite. It will use these different lengths and finally convert it back into your username proof. Field key is calculated using the formula field number into 8 plus wire type. Field number 1, wire type is 0, and so on. So you can get deeper into protobufs and how this encoding decoding is done. For our purposes, it's just enough to know that this is what has already been defined in the library, and on top of that there is an encoding decoding scheme to basically streamline it, like encode it into one standard packet and then exchange it across different hubs that are present out there. You could choose other variations also, but this is what has been implemented with Hub-Monorepo, so we'll be going with this. Just as encode, the opposite of that would be decoder, where you have a minimal protobuf JS reader. You get in like a reader or a uint array, you get in the length of the total message, and you instantiate the reader. If the length is undefined, the reader.length, you assign the length. Then using the message, you create a base name user proof. Okay, so basically you return this. This is the empty username proof, which will then be filled in by the values decoded from the encoded message. Reader position tag, and then based on that, like these tags are different lengths. Like encoding, I told you, like 8, 18, 26 that they have encoded here, 8, 18, 26, 34. So these are like different flags, like 8 will be here, 18 will be here, 26 will be here, 34 will be here, and so on. Similarly, in decoding, it will just do the opposite. Like at 8, 18, 26, it checks for the tag and accordingly reads the data present between two tags. And because it has already the structure, it knows what to look for. Like if the tag is not at 8, then break, because in case there is no timestamp, this will be working. Otherwise, you need to convert it from long to number till the tag 8. Similarly, reader.bytes, you read the message.name, message.owner, signature, FID, and so on. Similarly, if you have a JSON object, you can use that as well, and then you can convert this protobuf message into a JSON object as well. So I think the encoding decoding at protobuf level will be good for exchanging between the hubs, but let's say an external API needs to call it with a username proof, then therein from JSON or to JSON might come in handy. That is what my hypothesis is at this point. I don't know exactly for sure. Now this is from partial extends exact partial username proof. Okay, so let me quickly check this out. There's something to do with, I think, generics. Let's ask ChatGPT to explain this. Two additional methods in username proof object related to creating and manipulating instances of username protobuf message using TypeScript and protobuf.js. This function is a generic method to create a new instance of username proof with the default or provided values. Okay, so in case you already have provided values, it uses this. Generic type parameter I extends exact d partial username proof and I. Okay, this constraint ensures that the type I matches the structure of username proof but allows for fields to be partially set. D partial is typically a type that makes each property of the object and nested objects optional, allowing for incomplete objects to be used. Alright, this is pretty straightforward. So in case you have a username proof wherein you don't have fields, value for fields like timestamp, etc. Let's say you only have name and signature, name, owner, signature. You don't have an FID yet and so on. So in that case you can use this D partial. You can provide these partial values and then create a protobuf out of it. D partial is the type, right? Base question mark colon I. So this is like an optional parameter that can provide initial values for the instance being created. Alright, base is not provided, empty object is used as default. So D partial from username proof but exact I matches the structure of username proof. Return from partial username proof from partial base provider, empty object. Potentially partial data, default for any missing data. Generic type parameter. This is pretty straightforward. So one is create, one is from partial. What I am curious about is just getting a better explanation of this piece of code. This is a TypeScript learning step for me as well. I is a generic type parameter, right? Right. Extends is used in generic constraint, restricts the type I to types that satisfy the constraint that follows it. Alright, so I needs to satisfy this piece. I must be typed that conforms to structure defined by exact D partial username proof I. D partial username proof. D partial T is a recursive utility type. All properties of T and nested properties optional. Partial will make all properties of T optional, but not necessarily the properties of objects nested. Okay, so this is for nesting also, D partial. Great. Exact TU is a utility type that ensures the type U is exactly the same as type T. This is often used in Typescript to prevent excess properties and ensure an exact match in terms of properties between two types without an additional properties in U that are not in T. Alright. Enforce a given type U that is exactly the same shape as T. This is pretty clear now. That D partial username proof that we had created, any D partial, like all the parameters and the nested objects, like parameters inside nested value also is going to be optional. Once that is run, the type that is returned from this needs to be the same for I as well, and then on top of this I can also extend this. Restricts the type I to types that satisfy the constraint that follows, right? Makes all properties exact U and I, right? This is pretty clear now. So create from just a bunch of TypeScript magic. Declare var self any var window global TypeScript protocol go global this undefined self window global object. I think this would be happening in the entire hub level. Bytes from base 64. You give it a base 64 string, it will return you, or you enter your bytes. Just a bunch of utility functions. Base 64 from bytes. This is also fine. Type of built-in date function unit array, string number boolean undefined. Deep partial of type t extends built-in array deep partial. Okay, this is just some typing things. Long to number functions that have been used throughout this being defined here. So these are utility functions. This is all sorted. Fundamentally, username proof is just defining an interface and then having a bunch of encode decode from JSON to JSON functions on top of it to basically encode it into a protocol buffer message and then decode when you receive a protocol buffer message. Pretty straightforward so far. So we have done username proof. Then we saw that the message required a username proof, which we have done. So let's say you have a user, you generated your FID, you want to create a username proof on top of it. This is the underlying logic that will be used to transport, I think, the username proof as create as well. There's a create function in it as well. Now let's get into message. What does message say? Long username proof, type of hashing scheme used to produce a digest of message data. Again, simple hash scheme, none and Blake 3. So now your message hashing of this message can happen using none. It can be an unhashed message or it can be a Blake 3. Hash scheme from JSON. Straightforward, either you pick Blake 3 or none. To JSON, you give it none or Blake 3, it returns this string to identify the type. Similarly, signature scheme, none, ED 25519, EIP 712. Alright, then on top of message, you have a signature scheme. So basically, you hash it, and then once it's hashed, you sign the message. ED 25519, EIP 712. This is your ECDSA, which is compatible with your EVM ecosystem. Ethereum signatures. Signature scheme from JSON, you give it a JSON object, you figure out which signature scheme is being used. Again, to JSON, straightforward. Type of the message body. Now let's get deeper into message itself. So far we saw that message can take in a username proof. It can be hashed using these two, and then on top of the hashing you have a signature scheme for this. Now let's get deeper into message itself. Let's consider message. What we have seen so far is username proof plus hashing plus signature schemes. Let's zoom out a bit because I think there will be a lot of stuff in this module. This forms the heart and soul of mostly what happens across entire Farcaster. Actually, this is the Farcaster protocol specification in a way. We are seeing very similar things: encode, decode from partial base message data from JSON to JSON. Oh wow, it's over 1500 lines of code, I think. Yep, almost there. I think it's probably 3000 lines of code. So when reading a new code base, now always try to zoom out first and figure out the overall structure, like what are the different functions that are there. It just helps create a better mental model or a bird's eye view. Frame action body. I think this should be it. A bunch of utility functions. Yes, 2100 lines of code. Alright, let's walk through it quickly. Your scheme, scene hash scheme, signature scheme. It's time to see message type. So all this will flow into message itself. Type of the message body. Message type. This. Then this is your none, cast add, cast remove, reaction add, reaction remove, link add, link remove, verifications. And user data, frame, link compact state. Alright. So cast, reaction, link, verification. Fundamentally four parts in it. Cast, reaction, link, verification. User data add, user improve, frame action. Okay, user data add has been deprecated. User data add. Then you have user improve, frame action. In compact state, which I do not know what it is yet. This is what powers your likes and recasts. Link is what powers your follow, unfollow. Verification, I think this is what powers your owned addresses. There are a bunch of other things that we'll get into. User data add, message type signer add, remove an ed to identify signs a message for you. This has been deprecated somehow. Add or replace a user improve, Farcaster frame action, link compaction, state message, verification add ETH address. Okay, verification of an ETH address, right? If you own a particular ETH address, there's something you can verify here. Now once you have defined this message type enum, it's again straightforward. Like you provide a JSON object, from this figuring out which message type it is into the enum, and then finally when you like message type to JSON, you provide a message type and it returns the string. Now Farcaster network, the message is intended for this would be none, mainnet, testnet, devrent. This is pretty straightforward where the hubs are talking. Same thing from the enum to JSON, from JSON, user data type. Okay, so now user data add. This is basically all your bio profile information. This is going to be your none PFP display bio. Okay. None your profile picture, your display name, your description or bio, your URL and your username. These are all going into Hub-Core. User data type from JSON. User data type from JSON. Reaction type like recast, as I told you before. Same thing from enum to enum. Protocol to disambiguate verification address. So you can either use a Ethereum as well as a Solana address. Protocol Ethereum, protocol Solana. Right. Now once you have all this, what is a message itself? So you have all these different types of which this message can be. So message itself is very straightforward. It is a delta operation on the Farcaster network. What does that mean? That Farcaster network was, let's say, in this state at time t. You send a message or it emits a message. This message changes the state of Farcaster network at time t plus 1. So this message is what the change that happened, or the delta. Like let's say you have casted 100 casts so far. Then you cast your 101st cast. Your profile changes. The entire network changes, like all your followers get to know that you have casted 101st cast. Similarly, in the entire global state of the network, they get flagged. Hey, this particular person has casted 101st cast. So message is just a delta operation of one of these types. Now what does it carry? A message fundamentally carries one of the types that we have discussed so far, that if it's a reaction, link, cast, username proof, etc., verification proof, not username proof, what was that? Actually it was username proof. Alright. Username proof, or your user data, and so on. So one of these types, one of these types is contained. Second thing, it will have a body where for each type the actual content, let's say you have a cast, so what is the text of the cast? So the actual content, let's say it's a link. So link means follow, unfollow. Then who did you follow, that FID and so on. Reaction, like what did you like, so that particular cast's hash. the actual content, which can be the text of the cast, like hash or URL of the cast, like these may be a bit inexact right now. You can figure out what the exact body will contain, but for now, like hash or URL both works. Like link, so FID of the user that you're linking to, and so on. Signature for a username proof, verification for like a signature for proving that you own a particular Ethereum address, and so on. So what is the actual content? This will be your body. Then once you have these two, on top of it, it says wraps a message data object, contains a hash and a signature which can verify its authenticity. Nice. So this message piece inside has message data, which is what is going to contain this, and then this message data. Now let's say signed it. I am a user with an FID 1, username something. I was the one who emitted this message. But how does the network know that it was me, my particular FID, that emitted this message? So what it does is this entire message also contains the entire message also contains a hash and a signature. Like this message data is hashed, as we saw, based on one of the two hashing schemes, like Blake 3 or none. None, I mean, then it's not hashed, but I'm assuming that it's Blake 3 right now. And then this is then signed based on something linked to my FID. Okay, so this way you would know that this particular FID emitted this message data and it also signed it. That links this entire message data to this particular FID. This is the linkage that is happening. So once more, very quickly, we can recap this. You have a message data. Then there is a hash of it. There is a signature of it contained within this entire data packet, which becomes your message. The message data is your delta operation, or the change in the network. Hash your Blake 3 algo. Signature ensures that its authenticity is proven, that hey, yes, I casted this, no one can fake that. And this entire thing is what the message, which is transported between hubs via the gossip protocol piece. And this is the message, and this is heart and soul of Farcaster protocol. Alright, this I hope makes things a lot clearer for anyone looking to work on top of Farcaster protocol. Message is what is the crux of it. Now, the interface message, you have the message data, hash scheme, signature scheme, who is the signer, Okay, public key or address of the key pair that produce the signature. And then you have the data bytes. Message data serialized to bytes if using protocol serialization other than TS Proto. So you can either put data here if you are using TS Proto. If not, you can put the data bytes here. So just a bunch of layers on top of it. Underlying, you have message data. Now message data is going to have the type. As we discussed here, message data has the type and the body. Message type, FID, timestamp, network, cast add body, remove body, depending on, like, these are optional. Whichever the type is, that particular field will be filled in with the relevant content. And then you can dive deeper into each individual content type. Like user data body will have its own like subtype and a value. If it's an embed like a URL or cast ID, cast add body, the parent, whichever the parent cast is, like let's say you're replying to a particular cast, then it will have a parent cast ID while yours will be just a cast. And then these different permutation combinations are used to identify whether it's a reply, whether it's a cast itself, whether it's a cast in a channel, and so on. Identifier used to look up a cast ID, AFID of the user who created this, and the hash of the cast. Interface, reaction body, verification add address body again, address being verified for a given protocol. Let's say you have an ETH address, you provide that address, you provide a signature, you provide the hash of the latest Ethereum block when the signature was produced. So this works as some sort of a timestamp. Then type of verification, it can be an EOA or a contract address has been verified for the given chain ID, and the protocol I think would be Ethereum or Solana. Verification, remove body, address of the verification to remove, protocol of verification to remove. Now things, this claim signature produced by user's address for a given protocol. I think the block hash itself is signed, probably, because I'm not seeing the string that is signed, which can then be verified through that address. Let's check that out. Types, link body, type of link, user defined timestamp, that is the original timestamp, target FID, yeah. So that's why I told you that this link would have the body, like which FID you want to follow and so on. Link compact, some compaction message for link store, frame action. Similarly, URL of the frame triggering the action, index of the button pressed, cast ID, input text, state, transaction ID, and so on. Create base message. Okay, so I create an empty message just as we saw based on the interface, and then protobuf encoding decoding starts at 10, 18, 24, 34, 40, 50, 58 with the length of each individual field in the interface that we have defined. And then just opposite, you decode it, you create it from partials, create base message data. This is again same as the message data body, same pieces, encoding into a protobuf message, and then decoding from a receive protocol message from to create from partial. And then inside message data body, like the different data types are being covered. Like for user data, this piece is used. For embeds, this is used. Base cast, cast add body. So if you just create a cast, this is what is triggered. You can have a look into it. Like if there's an embed, if it's a mention, parent URL, message.text, so all your cast text is processed here. Same thing, cast remove, you want to delete a cast, this is what goes on. Cast ID, each individual cast ID is defined. This way you have a hash of the cast using the hash schema and the FID of the person who casted it. Same encode decode to JSON from partial, create, reaction body, like and recast, the two things that we had talked about depending on the message.type. Then create base verification address. Same thing, given address, claim signature, block hash, verification type, chain ID, protocol. Sorted. Verification remove, you remove an address you no longer want associated with RFID. Link body, link compact body, create base frame action. Okay, and a message that is of type frame action, and then encode decode for that. And finally a bunch of util functions on bytes from base64 from bytes. One thing that is interesting to me is why have they defined the same function in different modules, like why this repetitive code, and a bunch of TypeScript related stuff. So we quickly did message, we have done username, proof. Now let's get on to gossip as to how these messages are sent between. Yeah, so from the message it's pulling out Farcaster network from JSON to JSON and the message itself. So for the gossip protocol, it's again pretty straightforward, I think. Gossip version 0 or 1. Okay, so between the hubs that are talking to each other, this is the versioning that they have come up with through enums. So I think older versions might be talking with v1 protocol, but the updated hubs might be talking with v1.1. Again, this is just a hypothesis, please verify this. Gossip version from JSON, gossip version to JSON, straightforward. Gossip address info, like which hub address to talk to, what's the family, port and DNS name. Okay, contact info, content body, gossip address, RPC address. So this is just a bunch of like servers running and talking to each other with messages. Gossip RPC address, closed hashes, count, hub version, network, app version, timestamp body, signature, data bytes, contact info, content. I think signature of the message digest, fine. Public key of the peer that originated the contact info. Optional alternative serialization is for signing. Alright, ping message body, acknowledge message body, network latency, message bundle, gossip message. Right, so they are a bunch of servers that are run as hubs. They are talking to each other and they are in a way telling, hey, this is my address. They ping for a message, they acknowledge, hey, this message has been received, and they also validate, this is my signature, so that it's not spoof. Let's say for the hubs, this is very simple, like they are just a bunch of servers running together. Let's say this is hub 1 and hub 2. So hub 1 has a set of messages that came from here. Okay, let's say hub has a set of messages. You casted, you reached hub 1. Now hub 1 wants to send it to the rest of the network. Hub 1 wants to transmit it out. So it hits, let's say, hub 2. What hub 2 does is, in a way, says, yeah, I am a legit hub. This is my address, this is my contact info, like this is my URL, etc., where you can send me whatever message packet that you have received. And then they keep talking to each other. So the entire gossip module is just to enable that particular protocol, which I think is not very important from an application perspective for us, because unless you want to run a hub and customize certain things, you just need to let it run as it is, because this is the standard on which the entire hub network is working and talking to each other. Like network latency message, like you also keep checking, one hub might keep checking, hey, like sending a ping message to another hub, whether that hub is up or it has, like, let's say, gone down. Now hub 2 has a problem, or let's say a power cut, then this goes down. So when hub 1 sends in a ping message, it might fail, and so on. Or it might also check as to how long is it taking for it to send a message and then receive a response, to check the network latency. Message bundle, topic, timestamp, create base gossip address info. Again the same thing for the protocol buff. Encode decode from JSON to JSON, from partial base contact info body. This is all pretty straightforward. What the different interaction between hubs, contact info, content, message signature, data bytes, gossip address, RPC address, clues hashes, hub version. Yeah, this does not concern us too deeply. Ping message, network latency message, bunch of functions for the hubs to interact with each other and check their health at a network level. This is fine, we'll not spend too much time on this. Once the gossip piece is done, then what is left? We have on-chain event, request response, RPC. Let's quickly get into all that. What is hub event? Takes in message, takes in an on-chain event, username proof. Okay, so it requires an on-chain event. On-chain event type, none, signer. Give me a couple of minutes, I'll grab some water and be back. Yeah, so basically this is an on-chain event listener in a way. Like whenever something happens on-chain from a user, like an FID, it would keep an eye out for that. Let's say someone added a signer, FID was registered, someone bought storage for their rent status, I think. So the hubs keep listening to that as well. So on-chain event type from JSON, on-chain event type to JSON, signer event type. Okay, so if a signer is added to an FID, if you're familiar with Farcaster protocol, it has 3 on-chain smart contracts. One is where your FID is generated, one is where your signer or key is added to your FID, and third place is where your storage related stuff is mapped and maintained. So signer event type from JSON, again you pass in a JSON, it returns your enum. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for enum. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again everything that we have seen for ID register event type. This is again ever Okay, so if you registered a new FID, if you transferred an FID, if you recovered a particular FID, those are the event types that this module keeps listening to. On-chain event type, the type that we just saw, which is your signer migrated, ID registered, and storage rent, based on the which particular chain, block number, block hash, like a bunch of blockchain related information, transaction hash for the on-chain event, then log index, FID for the given Farcaster ID that this is happening, and then based on the type, a particular event body will be filled in. Let's say you do a registration, it will have a different event body compared to you doing a migration or an on-chain recovery or buying some storage. ID register event body, storage rent event body, signer migrated event body, and so on. Signer event body is, you have a key type, you have a signer event type, a metadata, and a metadata type. Signer migrated event body, you migrated at. Some of these fields I'm still a bit unclear, so we need to dig deeper, but this is fundamentally like the bunch of on-chain interactions with the three Farcaster protocol contracts, and then depending on those interactions, some event is emitted which the hubs keep listening to, so they can again gossip it amongst each other as well, and emit it as a hub event as well. You registered an ID with your recovery address, storage rent, base on chain, undefined event, transaction index. This is all pretty clear. Again, just the same encode decode for the on-chain event into a protobuf from partial signer event. What I'm curious about is what exactly is this key type? Key and key type. What exactly is this? Is it something to do with Solana and Ethereum? Or it is like a recovery versus primary? This is unclear so far. It's a number is what I know, but what does it signify? Yeah, rest all is pretty similar. Let me find if I can see a definition of key type. There's two types or two places mentioned, but no clear definition. Anyway, so on-chain event is also done. Now on-chain event and message combined are part of hub event. Long M0 message on-chain event and username proof. Now hub event type, the hubs are emitting these different events. You can merge a message, prune a message, revoke a message, merge username proof, merge on-chain event. Alright. These have been deprecated, these have been deprecated. Now this is very important for the shuttle package as well. The shuttle builds on top of this because it picks up the hub events. If I go a bit broader, this is what is going on. We had our message. Now this hub is picking up the message that a user is generated. This hub is also listening to a bunch of on-chain events. Okay. And once these two are there, like username proof also the hub imports. So hub essentially emits out hub events. Which are one of your 5 types. Merge message, prune message, revoke message. Merge prune, revoke, for message, and there is merge user improve and merge on chain event. So the hub events are emitted, and this is where Postgres comes, or shuttle comes into picture, where shuttle sets up a pipeline to listen to these hub events and put that into a Redis stream, which is finally put into your Postgres database, and then you can have a bunch of APIs, etc., sort of like Neynar, which is then used to serve outside world and build applications. This is the entire flow for Farcaster. Bunch of hubs interacting with each other. So the inner layer would be the hub, which in essence is messages talking to a different hub. These are all listening to your on-chain events. And emitting your hub events for anyone to listen. Like this also forms part of that. Gossip plus hub events. These hub events are then listened to by shuttle, gets into Redis, gets into Postgres, which is where comes your Neynar. So there is this inner layer of network which is emitting out stuff for the outer layer to build app from. I hope this entire piece makes sense. These are the 5 event types right now. Grab event type, merge message body, prune, revoke, merge interface. So merge user improve, then it has its own interface, user improve, deleted, user improve, etc. Hub event type, and then depending on the type, the different body that is going to be there. This is I have covered, I think, in shuttle piece also. Just all the hub events coming out, and then again a bunch of protocol serialization, deserialization on top of it. So hub event is done. A hub state. What exactly is hub state? Hub state is validate or revoke job state. Farcaster time epoch, timestamp where the last job started, last FID to complete successfully. Okay. So your hub is like continuously listening as well as sending out messages. It may happen that some hub might go down at a particular time. So hub state is where it's like a small piece of memory, you can say, where it remembers as to where it was last time. It lets it stop working and then continue from there. Last FID to complete successfully. Hub state, last ETH block, fname proof, L2 block, validate or revoke state. Same encode, decode, 2JSON, partial, hub state, right. Hub state, Okay, it also uses hub state. It would use in another way to process ki, hey, like let's say it has a particular state, this has a different state with respect to different messages. So it might use these two states to sync up and check ki, hey, let's say I processed till 5 p.m. today, and the other hub says that I have some messages that are after 5 p.m. till 6 p.m. So it will just ask, hey, can you like check what are the messages that I am missing, and then reconcile that. Again, based on high level reading, this is a small hypothesis. Please verify this, but I think this is what it will primarily be. Job. What does job do? Revoke message by sign a job payload update. Job payload, okay. Job is generally put in as some sort of a worker, the actual process that is taking care of whatever functions that have been defined out there. Let's see. We have done on-chain event, message, we have done hub state, we have done hub event, we have done gossip. Job we have put in a hold right now. Request response. It is support ENS names on the hub. Let's check. Just by signer job payload. I really don't know what this is doing right now. On-chain event. Yeah, we have done on-chain event as well. Request response RPC sync try. Okay, let's check what request response is. Contact info, hub type from JSON. You got the bunch of hub events, you got the bunch of messages, you got the on-chain event and everything. Store type. Uncast link, reaction date and all that. Store type from JSON. Subscribe request. Event type from total shards. Event request, hub info request, hub info response. Okay, so this is sort of exposing an API on hub. Like let's say you can subscribe to a hub and listen to all the events that are being emitted. Like this one, subscribing. This is what Shuttle uses. Here in Shuttle has a subscriber that calls a particular hub, you pass in the URL and tells that particular hub that, hey, I want to subscribe to the events that you are emitting. And you can also pass in a particular event through ID and listen to that. You can ask for the info of the hub, and then this is what the hub responds with. My root hash is this, my DB stats is this, peer ID is this, and so on. So this is again used for different hubs also to talk to each other as well. DB stats is, this is the number of messages that I have, number of ID events, number of name events, and the approximate size of my DB right now. Sync status, request. Alright, I think another hub with its own peer ID would call in, let's say hub 2 calls hub 1 with its own peer ID and says, hey, I want to sync with you. Then this is like, I'm syncing and so on. Sync status, peer ID and sync should sync, divergence, prefix. Okay, so they basically check their messages, our messages, and figure out whether there is a requirement for syncing between two different hubs. Try node metadata response. Try node metadata. So they create like tries and use the try to figure out whether you need to sync in with another hub, basically missing messages between two different hubs, and then use that for the diff syncs piece. Sync IDs, FID request. FIDs request, you can call the hub with a bunch of FIDs and check for their events. Messages response, casts by parent request. Provide in a bunch of cast IDs, parent cast IDs, and you get the casts by that. Reaction request. So these are used to, I think, expose APIs directly at the hub level, where you can call the hub and get a bunch of information like storage limit, user improve request. So all the events that hubs are proactively emitting, you can also call directly HubDB and then have index it and use it the way you want on top of it. Right, and then there's just the same bunch of encode decode from JSON to JSON bunch of methods as well as generics for all the types that we saw to be able to function. Let's get into RPC. There's nothing here. Sync try. This is also interesting. DB try node, key, children characters, items, create base DB try node. I think this is why used for creating tries. You need to read diffsync provided, diffsync explanation provided in the Farcaster protocol. So it's like you have a set of like hub1 has m1, m2, m4. hub2 has m1, m3, m4, m5. So you create tries and you try to figure out, like let's say these two are common, but the messages which are not available across both. You do this through tries and they have an algorithm called diffsync, differential syncing. So you figure out that, hey, I have m3, m5, but I don't have m2. This one says that I have m2, but I don't have m3, m5. So once they figure it out, they will kind of try to exchange this. Okay, I'll give you m3, you give me m2. This is what diffsync is. It takes a snapshot of the database at a particular point and then compares those two. Alright, so what we have done so far is the core package is done. We'll move into Hub Node.js after this in the second video. See you there.